think we're ready to introduce our guest speaker for today. So I am pleased to welcome Renee Collini this afternoon. Renee has a dual appointment as a coastal climate resilience specialist with Mississippi State University and Mississippi-Alabama Sea Grant Consortium. She's focused on sea level rise and helps facilitate the flow of information between researchers and decision makers to really make sure that science gets applied. She's the program coordinator for the Northern Gulf of Mexico Sentinel Site Cooperative. She's collaborated on numerous projects that have helped to improve coastal community and environmental resilience. And she's a recognized leader in resilience across our whole region, the Gulf of Mexico. So we're really lucky to have Renee with us this afternoon. I think she's just the right person to talk to us about sea level rise models and how to use them. So Renee, on that note, I'm going to pass the microphone to you, and I'm going to turn off my video as Michaela instructed.
Thank you, Marion. I just want to double check that y'all can hear me and everything's good in that respect.
We can hear you.
Awesome. Okay. So yeah, I'm here today, as Marion said, to talk about why there are so many sea level rise models. To give you a sense of where we're headed, first I'm going to do a review of the types of sea level rise models that are out there. And while I'm doing that, I'm going to talk a little bit about when to use them or how it makes sense to use them, and then some tips and tricks as we go along the way to make that a little easier. Then I'm going to pull up some examples of common models that I think people have seen, or tools that people have seen, and talk about the kind of models that are in them, just as examples. And I'm going to keep saying this, but that list is not exhaustive at all. None of this is exhaustive. And then, as Marion mentioned, there'll be time for questions at the end, but several points throughout this, I'm also going to stop for questions. So as soon as you have one, drop it in the chat box. This kind of thing builds on itself, and I want to make sure we're all staying in it together, and I don't want to leave anybody behind. So I'm going to stop frequently to answer questions. All right, so to jump right in, I think people have this idea in their head. If we're talking about sea level rise models, then it's just like this, right? The water goes up. This is a model. Ta-da! Now I have a model. I think we all know, though, there's a lot more that goes into it. If it was that simple, there wouldn't be what feels like a million different types of sea level rise models out there. So when you boil it down into all the different pieces and things and efforts that are out there, sea level rise models seek to answer one of two questions, sometimes both. The first is, how much will water rise? How much is mean sea level going to go up? The other question is, what happens when this mean sea level rises? How do things change? So we're going to take models that answer each of these questions one by one. We're going to start with, how much will the water rise? And the models that work on answering that question. So when we're saying how much will the water rise, we're talking about models that project an increase in mean sea level. And a term or a series of terms you may have heard associated with this is probabilistic versus scenario-based. So when we talk about probabilistic models that project how much mean sea level is going to go up, they're defining a likely range. Not every set of probabilistic models uses the same sort of range, but for example, the IPCC uses a 66% probability. So that means that there's a 66% chance that sea level rise will end up somewhere in that range. But an important thing to note about this is that means that roughly 1 in 3, you have a 1 in 3 chance of the sea level rise we'll actually observe in the future not falling within that range, that it could in fact be higher. So for people who are planning for, say, really risk-averse type things, the example they gave in a recent report was if a nuclear power plant was being designed for, you're not going to want to run the risk that there's a 1 in 3 chance water will be higher than what you're planning for. So then there are these scenario-based plannings, and it has a very applied context. So it's taking that range of what's possible at its almost entire range. And this wider range is for those who are less risk tolerant. And so I'm going to just sort of give a quick display of what that looks like in hopes to help make this a little more accessible. So you have these conditional probabilities. This is all the things the water could look like under what's known as the RCP, or the representative concentration pathway. Just know that's about how much carbon's in the world, right? So say there's this much carbon in the atmosphere, this is how much sea level could rise. If it's a little bit lower, it's this much. If it's even at the lowest, this is how much sea levels could rise. You've got feet here and time there. With probabilistic modeling, they take this 66% chance. So this is the total amount that water could rise. They take this 66% amount, have this central estimate. So probabilistic is really focusing on what's most likely. When we're talking about scenario planning or scenario-based, they set these balances, the highest and the lowest, and then develop ranges in between, and then give probabilities that you'll see each of these. And that allows people to plan thinking about their own risk tolerance. I think many of you have seen me give that particular talk, maybe many times, but I give a whole other talk about how to use those probabilities for risk-based or scenario-based planning. And so when you're thinking about how these models project how much water is going to rise, you want to understand if it's a probabilistic model like IPCC, or if it's scenario-based like, say, the NOAA ones that came out from Sweet et al. In 2017. Because you can tell there, that's a big difference in range, and neither one of them is necessarily the right way or the wrong way. They're just looking at this from a different angle or approach. So that we were just talking about is understanding how much water could rise across the whole globe. But there are other things that influence how the water will rise locally. So what we just showed was eustatic sea level rise. And the way I keep track of this in my own head is I think about like the global mean sea level rise, how much just the water is going to go up. But this still impacts us, right? So we need to know what's causing it. There's two primary causes for that global rise in water. One is melting land ice. The other is thermal expansion. So these two things right here, melting land ice and thermal expansion, contribute to this overall global mean sea level rise. But then there are other things regionally and locally that influence the actual water level or the land that make sea level rise look different in each location. And these are kind of wild. So one is changes in gravity field. And I'm going to get into each of these one by one. The glacial isostatic rebound, and then plate tectonics or sediment compaction. So let's get into these one by one. So changes in gravity field. When I learned about this, it blew my mind, which is that as those giant ice sheets melt, they actually change the mass on the Earth, which means it changes the gravitational field. And so, for example, each one of those melts changes the gravitational field in its own specific way. And so with the gravity and a lot of mass with those ice sheets up north, for example, it pulls a bunch of water towards it. But as those ice sheets melt and get smaller, not only do they put more water in the oceans, but they relax that gravitational pull and it redistributes the waters in the ocean. And so as you can see from this is a graph that shows the breakdown of, say, Greenland or the West Antarctic or the East. And you can see that the redder it is, the more water it puts, it changes where the water is distributed. So really almost anywhere in the US, you're looking at more water showing up because of this, but it's not exactly the same everywhere. So when you're thinking about how much water will rise, you want to understand if that projection you're looking at considers this. And then here's just another example of, if you look at all of this combined, what that difference is across the US from that global mean sea level rise. You can see, especially along in the Gulf where we all are, and then I know we've got people from across the US, but it's a little bit higher pretty much everywhere for us. Then there's glacial isostatic rebound. And so if you think about the Earth as being like an orange or like a mattress, when those glaciers are heavy. And so back during the last ice age, when they were sitting on the land, they're pushing down. And so when you think about when you push on that orange, where the heavy thing is, your finger, it goes in, but there's this bulge that comes up on the sides. And so as those ice sheets have retreated, slowly over time, we're experiencing that same kind of rebound, right? The bulge that was up is going down, and the people who are being smushed, the land that's being smushed goes up. And so that's another factor that could be included when you're thinking about how much sea levels will rise, is this glacial isostatic rebound. And then the last thing is actual really local things is plate tectonics and sediment compaction. So if this is just a visualization, a conceptualization of what the land might look like, if you begin to have just generally sediment compaction, think about like in Louisiana with all those softer sediments compacting down that are recently deposited, but also pulling out of oil and natural gas or overpumping of groundwater. And in some places, earthquakes. I forgot about this because where I'm at, there's not a lot of those. But in other locations, like in America's Samoa, for example, they've had a big change in sea level rise locally because of earthquakes. But so what happens is, for all of these reasons, the land starts to push down and compact. And so then as sea levels rise, that land is farther down, and so the water is higher over that specific space. And so you want to make sure to understand if all these things are being considered whenever you're looking at those projections of how much water will rise. And so just to recap, when you're thinking about how much the water will rise locally and models that can project that, they'll include this eustatic sea level rise from the melting land ice and the thermal expansion. And they may also include these climatic effects from the actual ice, the gravitational field changing, from the isostatic rebound from the glaciers, and then also the localized vertical land motion, if you will. And so all these things together help project how much water could rise locally. So just to sort of recap, remember, there was two types of models overall with sea level rise. The models that tell us how much water might rise, and then the models who tell us what could happen if the water rises a certain amount. So to recap the ones who tell us how much the water could rise, these are projecting that increase in mean sea level. And so they can show global averages when you look at those projections, or they can show localized or adjusted for local influences. It's also important to understand that these are regularly updated. So science improves, it gets better, particularly around that global ice sheet melt. As that ice sheet melts and the rate it's happening, we're learning a lot about that still. There are a lot of papers that just recently came out, and so we're going to get another update soon. And the other thing is that we're getting additional observations. If you think about a weather forecast, you know, the weather that's happening on that 10-day forecast at the end of the 10 days, you're like, yeah, but that'll get a little tighter and a little better, versus the thing for tomorrow is a lot closer. And so it's the same idea. As we get closer to whatever our timestamp is, we can observe what has happened to understand sort of what curve we're on. And just some general tips or tricks, if you will, for when you're trying to understand what you're looking at or which kind. It's always better to use localized rates over global, particularly in the Gulf of Mexico, because we are at a higher than the global average rate. You saw those fingerprints from the changing gravitational field, for example. We are expecting more water rise than, say, the global average. So it's important, if you have them, to use those local rates, which we do for the whole US. And generally, if it's regionalized, you don't have to bend over backwards to find out. This is relatively newer. People are proud that it does that, so it should generally just state it somewhere. If it doesn't say that it's regional or localized, you can probably bet it's not. And there is no single authoritative on best scenarios. We talked about how sometimes it's probabilistic, sometimes it's scenario-based. Those have totally different things that go into it. There's also a whole other world of, do you use empirical models or semi-empirical or process-based or expert elicitation? And so there isn't a best scenario, but there are some authoritative sources. The IPCC, the National Climate Assessment that comes out from the US Global Change Research Program. I think you've heard of the National Climate Assessment 4, which was released in 2017 and 18. And then there's also regional groups that have dug in on what their local impacts will be and gone even farther than some of those things I've shown. The state of Washington has some. The Southeast Florida Regional Climate Compact is another good example. So you can go to groups like this, or people like myself. I think Libby Carnahan's on the phone. I'm not going to go through the whole list, but there are people who work on climate resilience specifically through Sea Grant and other extension sources. So in addition to these authoritative science sources, you can also turn to your local extension agents to help. So that was a lot, just dealing with that first type of model, the models that project how much sea levels may rise. Are there any questions about that part? What questions do y'all have so far?
That was a lot of great information so far, Renee. I haven't seen anything pop up in the chat window related to the content, so we'll give folks just a minute to chat their questions if they have one. One person did ask already if you are able to share slides, and I know that we are sharing a recording of this, but are you also willing to share the slides?
Yeah, absolutely.
Okay,
and
that's great.
I'm learning my lesson from advertising. I mean, from not advertising, from animations, not having so many. So it's easier to share with people.
And then I did get a question as well. We were asked if you could clarify what RCP is, or R.
Yeah. So the RCP are the representative concentration pathways. Jim, if I'm wrong, chat it in the box. But essentially, they're representing carbon emission scenarios, futures. sort of like we have different scenarios for sea level rise, there's also different amounts of carbon that could be in the atmosphere because that's based on people and people are still doing different things. And so that's really hard to predict. And so the sea level rise projections have to take into account how much carbon emission is going to be in the atmosphere, because those carbon emissions directly translate to warming, which means how much thermal expansion and how much ice sheet melt we're going to have. And so that has to be taken into account. I usually have a bunch of slides on that, but if we still have questions about it at the end, I can quickly pull one up and show you how that might influence. For example, like the really high carbon emission scenario, the RCP 8.5, it is 100% likely that we'll see the low scenario, but on that low carbon one, the RCP 2.5, it's like 90-something percent, it's lower. So yeah, I hope that was clearer and that works. Any other questions come in so far? If not, I'll just keep rolling.
I think we can keep going.
Okay. So now we've talked about the models that project how much the water is going to rise. But the other side of that coin is what happens once the water comes up or as the water's coming up. And so there's a whole host of models that can tell us or hope to tell us or inform what could happen when the waters rise. And so when we're talking about these models that look at what happens when the water rises, they're really looking at given a certain amount of increase in that mean sea level. So they're not trying to project how much the water goes up. They're saying if the water goes up X amount, they can tell us that they can project changes and say high tide. What is high tide going to look like if mean sea level goes up by 2 feet? Same thing with storm surge. If mean sea level goes up 2 feet, how will storm surge change? This is where I think another set of words often come up, bathtub versus dynamic, sometimes static versus dynamic. And so I want to take just a sidebar really quickly to talk about these words and what they mean here. So when you hear the phrase bathtub model, we're really talking about models that hold the shoreline itself static. They just simply elevate the water level. So if we're talking about future high tide, they keep the shoreline the same and they raise the water 2 feet. Now keep in mind when you're looking at this, it's not trying to get into things like how much erosion might happen or how people might change what's built there, for example. It's just, okay, the water overall is this much higher. And the dynamic models look at those changes. They start to think about, okay, well, if water comes up, it's going to interact the shoreline differently. It's going to cause erosion or change the shape of things, or it might change the health of certain habitats. And so this is a good conceptual example of what a dynamic model takes into account. And so it shows over time how things may be changing, how the shoreline may be changing with that much sea level rise. And so, for example, here, if you look at a storm surge model that's dynamic, like this one, it slowly changes the shoreline and then puts the storm surge on top of it. This isn't just for sandy shorelines, though. Here you can see an example of that same kind of conceptualization for a marshy shoreline. So it takes into account, again, the water's a little higher, the tide's interacting, there's erosion or other kinds of changes because of that. So this is a lot more computationally expensive. It takes a lot of computing power and a lot of research to even have the inputs to understand what these changes will be, because each location is going to be a little bit different. It's very advanced modeling. And so it's important to keep in mind, which one do you really need? It depends on the kind of questions you're asking and the kind of work that you're trying to do. So back to where we were talking about the kinds of models that project what will happen when water gets to be a certain height or as it becomes a certain height. Some examples of this, that they can project changes in high tide, they can project changes in storm surge. There's also a lot of models out there that look at how a habitat's extent or location might change, if it might migrate, how it's going to migrate. There's also those that look at the functionality of the marsh or the habitats or the health of those habitats. And then there's those that can identify things based on rising water. So for example, they can identify economic impacts from increased flooding, from those changes in storm surge, from those changes in high tide, and looking at that stuff that's being impacted and what that might cost. Additionally, you can identify critical infrastructure that's at risk. Our stormwater outfall is going to be underwater. Our roads are going to be more vulnerable. You can start to look at those kinds of things, along with the big things like fire stations, police stations, houses, schools. You can start to really understand what's at risk. And so there are models that specifically take those first models up here, the projected changes in high tide, and then start to understand what's at risk or what could be impacted by that. And then same thing, there's also the whole other section of people, populations, and demographics at risk. And there are some models that actually start to project those changes of where people are going to move and what they're going to do, and then how sea level rise could impact that. So I'm just reiterating this because I think sometimes there's some confusion. These models are not predicting how much water there's going to be. They're taking those curves, those projections of how much water there's going to be that we talked about earlier, and then they're looking at what changes may occur because of that. And so I just wanted to make sure we're all on the same page about that. So now I want to talk about some tips and tricks on the models that predict changes in tide. So again, you want to determine if there's any dynamic features. Are they looking at erosion? Are they looking at how the shoreline is going to change? Or are they just sort of holding things static and just saying, whether it's the water coming up or the land going down, you've got this much more water over the land, and that's what high tide is going to be. Different viewers of sea level rise generally have different purposes. So sometimes they are specific for identifying transportation. That's a lot of what the GeoPlan sea level rise sketch tool is about. Then there's the sea level rise viewer from NOAA, which we'll look at, and that one's really focused on just visualizing what high tide will look like under certain amounts of sea level rise. And then the other thing is, I keep mentioning mean high water, but other viewers show other types of tides, right? Whether it's high tide, mean sea level, lower low water. So when you're looking at these viewers, just kind of gut check if it's not jiving with other things you've seen. Understand if you're using even the same data. Now, when we're talking about storm surge, again, you want to think about that. Is it dynamic? Is it a static model? Are they looking at how the shoreline changes? And then you also want to check on which kind of storm they're talking about, right? So some of them do that annual chance stillwater, that 1% chance event or the 0.2% chance event. Some of them look at historic storms, and then some of them just look at, so category 1 here, how much surge would you get? Category 2 here, how much surge would you get? So you need to make sure you understand when we're saying surge, because we all know surge is really dependent on the storm and location. So make sure you understand what kind of surge you're talking about. And then you also want to make sure that they're actually talking about future storm surge. So some viewers or sea level rise tools will show sea level rise on one tab and then storm surge, or sometimes they even overlap. That does not necessarily mean that that is talking about future storm surge. There are cases like the Coastal Flood Exposure Mapper. That one shows sea level rise as one hazard, and then it shows storm surge as a separate hazard. It is not showing what future storm surge will be. So make sure you're checking that out and you really understand what you're looking at there. And again, the people who make these tools are always happy when people are using them. So if you just give them a call or an email, they can probably clarify for you pretty quickly if it's not apparent when you look around. So talking about those models that look at habitat change. These models usually have a very specific focus or a specialty in a certain kind of habitat. You want to make sure you're talking about a model that's designed for your habitat or optimized for your habitat. Some key things to understand, especially if we're talking about like vegetative habitats like marshes or mangroves or upland forests, you want to understand why the model says this is no longer a marsh, it's open water, or this is no longer a forest, this is marsh. And so usually it's about the amount of time that little square has water over it. But you just want to make sure you understand that if at all possible, because that's going to help you understand a little bit about how the model functions and why. Another thing is the digital elevation models. For those of you who don't get into habitats, don't worry about this, you can blank out, but the elevation that's input, or the DEM, on these habitat models is very, very important. So you just want to take a look and see, okay, is this an older one? Is this from like 2012, or is this shot with the new stuff from 2017, which is a little more accurate? Because that's going to help you really understand what the input looked like and how close it reflects to reality. And then another thing is with habitat in particular. So with some of these flood models, it's a little less important, especially if it's sort of a generic planning level. It's less important how much time has passed if water is that high. Dynamic stuff, it does matter somewhat, but when you're talking about habitat, the amount of time matters. So for example, with marshes can't keep up with really fast sea level rise, but they can keep up with a little bit of sea level rise over time, right? They can accrete and grow up. And so it is important to look and see if there are time steps available, because it could be that while you've got 0.0 and you've got 2100, that maybe there's interesting things happening to your habitat over time. So don't just look at the endpoint and look at, what happens in 2100, but look at those steps between now and then to get a real understanding of how your habitat might be changing and what you might want to be managing for. Economic modeling, not that common yet. I know of one that's out there and it's not even fully available yet for the Northern Gulf. It's becoming more common, but just keep in mind as they become more common and they're available that all of them have different assumptions. They're for a different purpose. They focus on, a certain question, because just like with other types of modeling, economic modeling can't be great at everything. So they're going to spend a lot of time and energy on really focusing on certain aspects, but there may be assumptions in other ones. And so this is an area where it's really important as these come out to just sit and have a conversation or read the data that come with it. And then when we're talking about vulnerable infrastructure, it's the same kind of thing. When these things are being identified, you want to know what data set went in or where they got those data from to identify those vulnerable areas. And oftentimes it's easier, for example, to just take the changes in surge or the changes in high tide and put that into your own layers if you work for a government or a municipality, because you're going to have generally more updated information. And it's also important when you're looking at these viewers that identify what's vulnerable to changes because of sea level rise, you understand what kind of flooding we're talking about. Are they talking about high tide? Are they talking about what's vulnerable because the tide is higher? Or are they talking about what's vulnerable because storm surge has changed? So digging into that and making sure that you're understanding what type of flooding we're talking about that your risk is increasing for. So just to do a quick recap, there was a lot of different things there, so I can't recap it as in detail as I did before, but the models that are showing changes with a certain amount of sea level rise show changes based on the amount of water that is increased. They can cover a wide range of models, some that are focused on high tide, some that are focused on future storm surge, some that are focused on how the habitats changed, and some that are focused on taking those other kinds of changes in flood risk, changes in habitats, and understanding other things that may be vulnerable because of that. The specifics of these different models can take you from just sort of a generic, like that's a pretty map, all the way through to really understanding if this is suitable for you or understanding to what level you should be relying on or applying that for different kinds of decisions. Okay, so that was the second type of model. So the first were projecting how much water. This one is talking about what happens if we have that much water. What questions do y'all have about what we've gone over so far?
I really appreciate all the tips and tricks and considerations that you've shared so far, Renee. I think that's very helpful. I know that a question came in for Michaela, so I'm going to let her share that question.
Thanks, Marianne. So yeah, we got a really good question here. So bathtub modeling appears very simplistic and likely to yield an analysis that is incomplete. Who or when does a bathtub model make sense to use versus a dynamic model?
That's a great question. There's the really sort of first level of that is if you're doing an initial screening or identifying vulnerabilities, especially when we're talking about changes in high tide, that is generally going to get you where you need to be, because you're not going to build something because of that, right, necessarily. When you're moving from understanding, identifying vulnerabilities, that sort of surface level, and really starting to dig into changes that are happening or designing things, implementation phases, getting into the specifics of that kind of stuff, that's when you want to invest. And I say invest because there are not a lot of dynamic models. Again, for them to be worth the effort, you need really local, small scale data sets. And so that high resolution is expensive, and it's better to do that in a specific location. So I would say the quickest tip is screening level versus implementation level as a good rule of thumb. Now, there are always going to be exceptions to those rules. If you have a unique situation, I would just throw out the majority of coastal Louisiana as an example to that, because they have so much subsidence going on that it could cause some pretty serious changes. But they have their own models there, so that's okay. But then there's also, of course, considerations for groundwater, or if you have unique hydrodynamic features, which is where just because of where you live at, say the water doesn't necessarily just come up, but it might do weird things, which is sometimes common in these bays and bayous. You might want to just keep an eye on that if it looks really, really wrong. But all of these things are getting better. So for example, the sea level rise viewer is a static model, but their DEMs, their digital elevation models, are a lot higher resolution than they used to be. They just didn't update. And so even that small change gives you a big improvement in that performance of that model. So in a nutshell, screening level versus implementation would be one. And then if you have a really unique feature that you might want to consider. Any other questions, or if that didn't help at all?
I don't see any other questions in the main chat. Michaela, do you have any others?
I do not, but I was told that was an excellent response.
Great, okay. Well, I'm going to keep rolling. We only have about, well, I'm hoping to be done here in about 10 minutes or so. So I'm going to run through these examples pretty quickly. And the goal here again is I'm not trying to be exhaustive. There are so many models out there and so many efforts ongoing. I just wanted to pull a couple common models or common tools to talk a little bit about where you might see these things I've been talking about. So the first one I'm going to pick on is the Sea Level Rise Viewer, which I think is fair because I work with it a lot. I love this model. So when you get to this screen, this is just what it sounds like. It's a Sea Level Rise Viewer, but there's some key things to point out. For example, it tells you right here, MHHW, that's mean high or high water. They're talking about changes in high tide. So just that little bitty signal helps you right away start to frame this. Like, okay, this is the highest point of a regular tidal cycle. Another thing is that it has 10 different feet. Again, this does not mean that you're definitely going to have, or they're projecting that you're going to have 10 feet of sea level rise across this entire coastline. It's giving you flexibility. So if you go and find, say, a planning range, you want to look at 3 feet of sea level rise over the next 30 years, you can go and change this to 3 feet and see what high tide may look like. Another thing is that this model identifies these green areas, which are low-lying areas. And so right away, that should signal for you a goal of this viewer is generally to identify low-lying areas. This is really to help people with planning, identify where you could have problems. Even if it isn't necessarily connected to the tidal areas, if they got water in it, it's going to stay there, it's going to cause same kind of problems. So overall, this viewer's goal is to identify low-lying areas that are going to be at risk to water. But the Sea Level Rise Viewer is actually getting a little tricky here. So that first place we were, I'm going to just point out here, this is just plain sea level rise over here on the left. But they have this thing called local scenarios. They've actually integrated those projections of how much water might rise. So, and these are regional projections. So I'm just to recap, they're looking at the projections of water and not just the global average, but locally. And so if you click on a specific location, I selected Dauphin Island. So this is relating back to projections of rise locally for Dauphin Island. And so what you see here is, again, mean high or high water, and it's looking at how many feet of water you can expect at different time steps if you're looking at this intermediate high scenario. So remember, this is scenario-based. It's not probabilistic because it has all of these scenarios here. So we're looking at scenario-based, intermediate high, and it's telling us how much water we can expect over a time frame. So this viewer actually goes a step further and doesn't just show you how much high tide might go up, but it also combines the how much water can we expect question, but it does it very explicitly. And so you want to look for things like this. When they start to combine time and scenarios, then they're moving away from just, agnostically, like this is what water looks like if there was 8 feet of it, and start to provide some information about how much water you can expect reasonably at that specific location. Some other common viewers, again, not an exhaustive list. This is why we have Gulftree, because there are so many. Climate Central Surging Seas, the GeoPlan Center's Sea Level Scenario Sketch Planning Tool, that's for Florida only, and again, that's really focused on transportation. The Louisiana CPRA Master Plan Data Viewer, and then for those of you in Louisiana, Jim Paul's on here, you can message him. And then there's the Coastal Resilience 2.0, which also has a high tide viewer. So now I'm going to switch gears and I'm going to show you an example of a future storm surge model. This one's called GOM Search, and it covers Mississippi, Alabama, and Northwest Florida. And so this one's presented in a story map. It's a little different than the last one we saw. And so there's different pages that talk about different things. And so the first thing to note is it tells you directly, this is a dynamic model. It's not static. And that's a thing, just like with those regionalized sea level rise projections of how much water could rise, when we're talking about models that are dynamic, they're proud of it. It is computationally expensive, it's taken a lot of time and effort and money, and so they're going to probably let you know as close to upfront as they can why this particular model is more advanced or that it is dynamic. The other thing is when we look at this viewer, and we talked about how there's different types of storms they could cover, this one is specifically looking at Katrina. It's showing you what Katrina would look like under 4 different sea level rise scenarios. Keeping in mind, again, this is a dynamic one. So they looked at how the shore would change with that much water, with that much sea level rise, and then they put storm surge on top of it. And so it can get complicated. You want to think about all these things as they build on it, but it's a dynamic model and it's looking at Katrina. The other thing that they showed here, just to give you an example, is they're doing still water storm surge. And so it's the 1% and the 0.2% annual chance. You can hear that in your head as the 100 or the 500-year floodplain. I'm trying really hard not to use that language anymore because it's not really reflective, but you get the sense, right? 1% and 0.2% annual chance. Again, you didn't have to hunt for this. This wasn't hidden. You know, they had Katrina earlier in this story map. Now they're showing you these floodplain changes. And so just look for those keywords to understand what kind of storm surge you're looking at. And then there are not very many models that show changes in storm surge. There's coming up, there's more of them coming, but there's just not a lot that exists right now. So the Alabama Coastal Comprehensive Plan has a map viewer that has that. And again, they have different types of storm surge. They have smaller storms with sea level rise. And then again, the Louisiana CPR Master Plan data viewer, I'm almost positive has future storm surge. I kind of rolled the dice on that one. Then there's also for Isla Mirada and the Keys, they have a specific map viewer that looks at how their future high hazard area will change as storm surge changes with sea level rise. And then upcoming in South Florida, there is a model coming from Peter Shen and his team. And then the Army Corps of Engineers is doing a project called SACS, which is the, I shouldn't have gambled at Southeast. They're looking at the coastline, the whole coastline, and they're looking at how storm surge will change. And they're actually going to even go all the way out to understanding what the economic impact of that is. But those last two are not out yet. So now I'm going to show you, I'm going to switch gears and talk about, give just an example of a model that explores how habitat could change. I'm going to go with HydroMem just because it's one I'm familiar with. So the first thing you should notice when, again, you go into their story map or their information is they are really happy to tell you all about this. And so for those people who understand this, what I usually glean from this is they're telling you the inputs, right? And so I can see that they're looking at tides and they're looking at the biomass of the marshes, that's cool. And they're looking at sea level rise and other things. And they're looking at accretion and elevation and the biomass productivity. So that's all that's what I glean from that, right? Like these are the things that are going in. And then they also use some words, narrative, for people who maybe aren't as great at the model symbols to explain a little bit more about their process and how it works. And so you don't have to be an expert in models or be intimidated by this, but if they provide this kind of information, it's always good to glance and see what kind of stuff they're putting into these. And that gets back to that tip about understanding how it is that they're projecting these changes or what makes a change. So then when you get to some of their results, they're describing the output right there up front. Marsh productivity results. This is about the health of the marsh. How productive is it? And you can see here that the outputs are maps. And so they're including these maps at different water levels. Again, there's a little bit of sea level rise, a little bit more all the way through to 2 meters or 6.5 feet of sea level rise. And so this is just one of their outputs, but they're telling you right up front what it is. This is about marsh productivity, and these are the outputs here as they're giving you maps. But I mentioned that with habitat, how the habitat changes is just as important as what your endpoint is. And so they also have this output here that shows you marsh acreage under around 4 feet of sea level rise, but it tracks it over time and shows you what the acreage of marsh is and how it changes. And so now we have two outputs, the health of the marsh and the acreage of the marsh. And then if you could see this play, it runs through, this is 2040, but it does 5-year time steps all the way through from 2020 to 2100. And so you get to see changes in acreage and health over time. There are lots of habitat models, maybe not as many as the viewers, but there's still quite a few. There's SLAM, which looks at different kinds of fresh and saltwater habitats. There's Warmer, which was developed for marshes on the West Coast, but now it's being used over here for both mangroves and marshes, I believe. NOAA has a marsh model on that same viewer I showed you. They actually have marshes on there as well. There's the tidal saline wetland model. And so this one doesn't look at changes in function or habitat. It doesn't even look to see if the tidal saline wetland turns into water on that backside. This one is really focused on how it will migrate, or if it can migrate upslope as water level changes. There are also lots and lots of habitat models that have been developed by individual researchers across the different coasts in different areas. So I just want to take a few quick seconds, Marion, I promise I'm almost done, to talk about next steps after you have these models, and specifically decision support tools. So you want to move from seeing these models and seeing this information and integrating that information into what you're doing and acting upon it. And there is a difference between seeing those changes and making decisions. And these models, almost all the ones I showed you, don't provide information. They don't tell you what the decision should be. They provide you information to help you make a decision. And so some communities have been taking the next step so that they can actually integrate this kind of model output or model outputs to make those decisions. So one example, they're doing this in Santa Rosa County, for example. They are taking lots of different model outputs and integrating it into one tool where they weight and prioritize what they care about the most. And that helps them identify both threats that are upcoming across a variety of different hazards and changes, and also lets them prioritize how to spend their money when they're talking about flood risk. There's also adaptation pathways where you combine knowledge of how different things will change because of this sea level rise, and you can start to map out what your actions should be as you see these changes. And that's an adaptation pathway is one name for it. There's lots of different names for it. And then another thing is to take this information, such as how much change in storm surge you might expect, and think about what that could cost you or what your adaptation strategy could be. And then you can run a cost benefit analysis on several different ones to determine what's the most cost effective. And you can take that back to, say, your constituents, if you're an elected official or a municipal staff member, or to your own pocketbook, if you're an individual homeowner, to think about which strategy makes the most sense to prepare for sea level rise and save you money. So that was a lot. I'm happy to take any questions about any of that, or if specifically you had questions about the examples, both of how people have been using the information or about those specific examples, or if there's a model I didn't mention that you'd like me to talk about. Just drop it in the chat. And I see Brian Anderson had a question. So Brian's question was, how do storm surge models account for different angles of approach or landfall of selected storms? That's a really good question. On the example I showed you is two examples of how this is often approached. One is to use a historic storm that's meaningful to people. So for example, they used Katrina because in Mississippi and Alabama, where that model was run, that was very impactful. And so it's just showing how the storm of record could get worse, which is hard to imagine, is often how people will approach it. The other is, instead of using a specific storm, they use that flood exceedance probability. So with FEMA, there's the 100-year floodplain. That's not associated with a category 1 storm or a category 2. It's just, what is a 1% chance height of water? What's the 1% chance every year that the water would get that high? And so they get that by running a series of synthetic hurricanes, a bunch of different ones over and over and over and over again, to see, statistically, what is the 1% likely chance of happening. And so they do that to generate storm surge projections.
Thanks, Renee. I know Michaela also has a question for you on her end.
Yes, I got a couple. So first, are there sea level rise models available for locations outside the US, for example, Central America?
I have no idea. I would imagine that there are at least some. Yeah, it's a great question. I do not know, but you better believe I'm going to email some colleagues at NOAA and find out. If that person wants to get my email address and just drop me a note, I'll forward on and find out what I can find out.
Awesome. And then Another question is, does availability of data affect which model can be used? Is there a danger in fitting the model to the data?
Yeah, there's a saying with models, garbage in, garbage out. That's a saying for a reason. Data availability often can be a limiting factor, especially when we're talking about habitats. And you get into those more complex habitat models, you want some historic data, you want some current data on a lot of different things that go into that. For example, that hydro-MEM model I showed you requires a lot of information about the habitat itself. Now, that said, it doesn't mean you can't work to get a small grant to collect those data or work with other partners and teams who may have that data and you just don't realize. Data availability may be a barrier to overcome, but in the grand scheme of things, that one's not always a huge one. It's less complicated, I guess I should say, than some of the more complicated aspects of this that get into values and hard decisions.
Sounds good. That's all the questions I had, Marian. I don't know if you had any others.
No, I don't see any other questions in the main chat. So I think we're good. Thank you so much, Renee. That was a great presentation.